Hi, in this video we're going to go ahead and look more closely at the normal curve and its properties. So first is we already know that this curve is bell-shaped. We've seen that in a previous video, and we can see it in the picture on the right. The next thing to know is that this curve, the mean, the median, and the mode are all equal. All three of those values sit right in the center where that peak is. Next one, it has a single peak, so we would call this graph unimodal. One value has higher frequency or is repeated more often than the others. And 4, we know it's symmetric. Very specifically, it is symmetric about the mean. If I fold that curve about its mean, I should get two perfect mirror images. The curve is also continuous. So we are looking at continuous data when we're looking at normally distributed data. Remember, continuous data usually comes from something being measured, and it's a data that can take on decimal values or fractions, any number between a minimum and a maximum. Next one, we're going to pull a fancy term from probably one of your high school math classes, which is this curve has a horizontal asymptote at the x-axis. What does asymptote mean? An asymptote means that this curve is going to get closer and closer and closer to the x-axis, but it's never going to touch. It's like if I were taking steps towards a wall and I'm always getting half as close. Well, 1 meter cut in half is 0.5, 0.5 cut in half is 0.2.5, 2.5 cut in half is 0.125. That number is going to keep getting smaller and smaller and smaller. But if I keep cutting things in half, it never reaches 0. Because something divided by 2, where that something is not 0, is not going to be 0. So that makes the next one a little bit weird, and I'm going to ask for some trust, because the next property of this curve is that the total area under the curve is 1, or 100%. The area under that curve represents the total probability. It's what it means to be a probability distribution, and that should be a little upsetting because we just said that this curve never ends. It goes forever and ever and it never touches. How do we know it's equal to exactly 1 under that curve? And the answer is calculus. And I am assuming that most of you have not taken calculus, will never need to take calculus. So I'm going to ask that you trust me that the math does work out. One thing that will be helpful is another mathy term. There is an inflection point at plus or minus 1 standard deviation from the mean. So right here and right here. You're never going to be quizzed on what an inflection point is, but it's useful to know. An inflection point is where the curve changes from bending downward, what we would call concave down, to bending upward, which we would say concave up. So inflection points are where that curve changes from bending down to bending up, or bending up to bending down. Never going to quiz you on that, it's not on your test, but we're going to be hand drawing a lot of these curves over and over for the next 4 weeks, so knowing that helps you make prettier graphs. A couple of last things. First, in our last video, we know that this normal distribution follows the empirical rule, and you can see it marked out in the picture that I've provided. I can spell. And that helps us determine answers we get from our calculator, make sure that they make sense. And then I made a note about inflection points. Normal curve within 1 standard deviation, the curve is concave down. And then outside of 1 standard deviation, it's concave up. And we saw that. This is bending down. This is curving up. Okay. Important note, you should always label the x-axis as x or z. Tell me, did you plot raw data or z-scores? You should always mark the mean and 3 standard deviations out. And label those hash marks with the appropriate numbers. Now for the scary part. You'll see an equation here that looks absolutely terrifying. This is the equation that you do calculus with to show that the area under the curve is 1. You never are going to see this equation again. The only reason it's here is I wanted you to see what determines the shape of that curve. And there's 2 things. We know x is our data, that's our variable. I know pi 3.1415926, that's a constant. E is another mathematical constant, it's called the natural base. 2 is a constant. The things that are not constant in there are the mean and the standard deviation. Those 2 values, the ones we see when we label a data value as normally distributed, those are what determine its shape. So it depends on the mean and the standard deviation. The mean shifts the curve to the left or right. And I'm going to scroll up here. The mean indicates where the middle of the curve is, so if my mean is smaller, that whole shape is going to move this way. If my mean is bigger, my whole curve is going to shift that way, the whole bell shape. The standard deviation is where those hash marks are. So the standard deviation makes the curve wider or narrower. So if I go back up, if my standard deviation is bigger, this point is going to move out, this point's going to move out, this curve is going to get flatter, and those longer tails are going to be further out. If my standard deviation is smaller, these points are going to move in, my curve is going to be a lot tighter. So where I sit on the number line comes from the mean, how wide or narrow my bell shape is comes from the standard deviation. You're never, again, going to be asked to use that equation. I'm not going to ask you that on a test, but it is important to know what the mean and standard deviation do to the shape of the normal curve. All right, if you have any questions about those properties of the normal curve, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.